All right, everybody. Thank you for being here this Friday morning. I can assume it's a bit hard after 2 days full of DevOps, but thank you for coming anyway and for listening to me. I have a lot I want to show you today, so hopefully this will be exciting enough for the next 50 minutes. Now, first and foremost, who am I? Well, my name is Vasco. That's written out there and at the door. I've been building and designing software for the past 25 years and still counting. But for the purpose of this session, I believe that the most important part is what I am not. I am not a mathematician. I am not a statistician, and I am most definitely not a data scientist. Now, this means that I understand and I can explain a helicopter view of how machine learning models work, but I am totally, utterly unable to explain the intricate details of the mathematics that actually make them work. Although some people do wonder if anyone actually understands how they work, but that's a story for another day. Now, many years ago, when I was a teen, living in a small village in the south of Portugal, every month a library on wheels would show up. Now, I was a very regular customer. I would be reading adventure, I would be reading mystery novels, sci-fi, which kind of makes sense given the professional choices I've made. After all, it can be an adventure to gather requirements for software. Some bugs are a mystery that I believe not even Monsieur Poirot and what was her name, Miss Marple, working together could crack. And sci-fi, well, I believe we all can say that the state of tech, especially machine learning today, would be considered science fiction 30 years ago. Which also is not too surprising that I have written a book or two along the past. The contents of this session are coming out of this one. It's 1 year old. If you want to take a look at the table of contents, that's the link. And now that the shameless self-promotion is over, let's get to what we are all here for. Now, because there is some terminology in the script and code in this model, let's just go very quickly over the anatomy of your basic machine learning model. So the neural networks are composed by neurons. Each neuron has inputs and an output. Inputs have something called weights, which basically determine the importance of each input in calculating the output and are determined during training. The output has something called a bias. It determines the activation level of the output. And there is something else which is used, if not all the time, most of the time, is an activation function, which aims to give a non-linearity to a neuron's output, because as we all know, reality is non-linear. Our world is non-linear. In fact, nature abhors symmetry. Therefore, neural networks need to be able to represent that non-linearity. Some more terminology. When neurons are chained together in a way that there are layers of neurons in between the input and the output, then it is said that we are in the presence of a deep neural network. Otherwise, we are just in the presence of a neural network. If we want to use machine learning on applications, specifically on mobile applications, then we have two choices. Either we code the whole neural framework by ourselves, which is perfectly fine, or we use an existing framework. For the purposes of this session and the book, I have chosen TensorFlow for, well, no special reason. It is a well-known and widely supported framework. And for our intents and purposes, it comes with a mobile library, or let's be a little bit more encompassing a library that allows us to use models in other machines than cloud instances or desktop computers. This library, called the TensorFlow Lite library, not only has a smaller footprint, but also the models converted to be used with TensorFlow Lite can also be smaller and can be tailored to the architecture of the device that we are running on, including potential hardware acceleration features. And of course, it allows us to run inference on models on the device itself, which means that we can now design applications that do not need network round trips to invoke some model somewhere in the cloud, and particularly transfer no personal data anywhere. All data stays within the device, which can be an important advantage if we are handling anything that can identify persons. Now, TensorFlow has that name because data inside TensorFlow is represented as something called a tensor. If we are going to look up the formal definition of a tensor, it is so abstract that, well, I don't know about you, but I read it and I looked at it and said, yeah, what? It is indeed a generalization, but for our intents and purposes, and for anyone coming from a programming language such as Java, C, C++, Kotlin, whatever, we can try to make it a little bit more concrete. Now, the previous definition said that tensors were generalizations of matrices, which means that they have an order. Now, if we look at a zero-order tensor, then that's what we call a scalar in Java or C or C++. In TensorFlow, the order of a tensor is called its rank. Therefore, a zero-order tensor has an empty rank. A first-order tensor is, well, an array. Therefore, it has a one-dimensional rank in TensorFlow. The second-order tensor is a matrix, 2 dimensions, 2-dimensional rank. A third-order tensor is an array of matrices, which can be seen as an array of arrays, and therefore has a 3-dimensional rank in TensorFlow. And it is also very common in TensorFlow to have fourth-order tensors with 4 dimensions, and they are mostly used when we want to batch training data together. Now that we went through terminology, it's time to take a look at the first practical use of a machine learning model. Now, one of the typical uses of a machine learning model is classification. And what does that mean? It means that we are using a model to say whether the data it is being fed with belongs to any of a predetermined set of categories. The data set we use in this application has a long name, is the Fashion Modified National Institute of Standards and Technology dataset, a mouthful, and it is intended to classify clothing. Each image in the dataset has an associated label, which is a number, and in our application we then translate that number into something human readable. Now, it is pretty clear that we see that boot corresponds to category number 9, and we are going to show that as an ankle boot in our application. Now, this is a very well-known data model. It's used in many projects, and therefore it is available from TensorFlow itself. Let me just get this script running while we talk about it. It's going to take a couple of minutes to train the model. As you can imagine, it has nothing special. We load the data set, we split the data set into a training data and testing data. It is also intuitive to know that the testing data is going to be used to verify how well the model is running after each training run. We need to do some data manipulation The original images, they are grayscale images, which means that each pixel has a luminance value between 0 and 255. The model prefers values between 0 and 1, so we just do a simple scaling. It means the same thing. And now the interesting part is the model definition. Now, as you can see in the comment, that's not my model. There are quite a few layers, and layers in a model can be neural network layers, can be neural layers, or can be some other operation layers. Now, for example, the first layer is a convolution layer. Now, convolution is an operation which, in this case, is going to transform pixels from one image to the other, and the output pixel is going to be the result of an operation applied not only on the input pixel, but also on its neighbors. Now, the exact result depends on the operation being applied, but to give you an idea, this kind of convolutions are used often for sharpening and edge detection, which are important in computer vision. There is a max pooling operation. This is downsampling. I want to call out the dropout layer. The dropout layer is interesting because it modifies randomly the input data in order to set some elements to 0. You may wonder, why is this even useful? The thing is that when training a machine learning model, it is possible for it to reach a stage called as overfitting. Now, this means that the model becomes extremely good at working with the data that was used to train it, but the moment you feed it data from any other source, then the model is completely useless. It is really, really close to the training data, and that's not what we want. We want a model that can generalize. That's why this dropout layer, by modifying the input data, allows us to add some randomness, so to speak, and therefore prevent overfitting. Now, there are more operations. We have a dense network layer with 256 neurons, which finally is connected to a output layer with 10 neurons because we have 10 categories. The model is compiled. It is then trained. It's the fit method, which kind of makes sense. We don't want it to overfit. We feed it the data. It runs for a number of epochs, which means basically training iterations. How many training iterations? Well, until the model is good enough. It's a bit of heuristics. It needs to be evaluated periodically, and that's why I ran training on this one, because this is what we want to see on a model training session. We want to see the accuracy getting better and better and better, which means that the model does recognize data and it's getting good at it. And we also want to see the loss value becoming smaller and smaller and smaller, which means that the model is outputting less erroneous data. Basically, the loss function measures the rate of errors in the model itself. Now, training this model took only a couple of minutes because it is an extremely simple model and the data set is quite small. And now the interesting part. If we look at the Android application project, one way of including the generated model, it was converted. We are going to look at conversion on the next example. The model, I was saying, if it has enough metadata, it can be just added to your project as a machine learning model, and then some code is going to be generated that will allow us to simply instantiate the model, giving it some options. Now, the TensorFlow Lite library does allow us to define a number of options. In this case, for the sake of demonstration, If the Android version supports it, then we tell the interpreter to enable the Android's neural network API support, which means that if in turn the device has support for accelerated neural networks, then we can benefit from hardware acceleration. Using the model is deceptively simple. Now, the application itself uses the camera to Android API to analyze video frames captured from the camera in real time, which means that we need to first, well, convert the video frame from the camera into a bitmap, and once it is converted into a bitmap, then we convert it into a tensor that we give the model, and the model is going to output 10 elements. Now, each of those elements will contain a probability value that the object depicted in the image belongs to one of said categories. We then sort it and present it to the user. Now, the end result is something that is quite simple. If we just show it the image I have on screen, it correctly identifies it as a t-shirt or a top. I can also try to show it my shoe. I don't know what's going to happen. Well, it says it's looking at a trouser, which is also correct. It's a trouser is also on the screen. Now, this is indeed one of the applications of machine learning models, classification. The other one is, for our example, face verification. We are going to use a model that has been designed to work with faces. But now we don't have categories. So how does a face get organized? Well, the model is going to produce an embedding. Now, an embedding, or an embedding vector, if you prefer, is we can think of it as a set of coordinates that identify a point in a space. If we then process another object and the new coordinates become close to the original in that solution space, then we can say that they are at least similar. The example you have on screen is from another model that processes words. And if we look at the country and capital representations on a three-dimensional space, we can see that, for example, Spain is to Madrid, just like Canada is to Ottawa. But on the other hand, we see that Canada is far away from Germany, and so the same way Madrid is far away from Berlin, which allows us to say that they have no relationship between them. In a nutshell, again, we get a picture of a face, we run it through the model, we get an embeddings vector. Of course, that the embeddings vector, it needs to be to represent a point in a specific space. Now, in our case, we know that this vector is normalized in Euclidean space, which means that we can use the well-known Euclidean distance to know if the different points are indeed close or further apart. And then, if it comes beneath a given threshold, then we say we are looking at the same face. Now you can ask, well, how do I calculate the threshold? Well, it depends. If you build your model yourself, then your experiments are going to give you that threshold. If you use a pre-built model, which is the case here, then the authors in their research will have most likely determined the most appropriate threshold for their application. It goes without saying that it is always a good idea to test the thresholds first. Now, since we are using a pre-built model, I just want to show you what does an embeddings vector look like. In order to do that, I'm going to run this Python script that is going to load an image of a face, is going to run it through the model, and we can see the output. As expected, an embeddings vector is nothing more than a long array of numbers. This particular model produces an array with 192 dimensions, so that's a pretty big solution space. We see that the model is already normalized. The norm is 1. We don't need to post-process the data, and the model itself has been built to accept images which are 112 pixels wide and tall, with 3 channels, which means an RGB picture. Now, using this on an application is, as you can probably imagine, pretty straightforward as well, although it is a much more complicated model than the previous one, but still, why using it would be any harder? In this case, the model does not have enough metadata for us to get some code generated from it, but that's also not an issue. We just load the file into memory, and we instantiate an interpreter based on that model. The TensorFlow Lite interpreter then knows what to do. For the sake of completeness, we query some metadata from the model in order to know, for example, what's the expected image width and height in the model. And we set up our own image processor for, resizing and normalizing the image. And then we allocate the output buffer, which is going to receive the embeddings. Calculating embeddings is as simple as running the interpreter. We give it the input tensor, we give it a buffer for the output tensor. Done. Not difficult at all. And that also means the image, or I pre-registered my identity before, which means that it is indeed identifying me. Now, the interesting part is that, well, first of all, the value that you see on screen is the distance between the new identity and the identity that was already registered. And the interesting part is that, well, it is seeing, there's more in that image than just my face. In our code, the network is a bit slow now. In our code, we are using another model to extract faces from the image we are recording, which is interesting. Then we used the Google Machine Learning Kit to detect faces on the image that the camera is currently recording. We extract the bounding rectangles from those images. We extract only the faces because that's what the model wants to do. And this is an important point. The model we used is for identifying, for helping us in identifying faces, but not detecting them. And when we do find a face in the input image, we then run it through the model. Now, this is a classic case of using one model to help another one. And, well, guess what? It works. Which is also why in the example you have on screen, you can see on the right-hand side that 2 faces were detected, but only one of them was identified. Another interesting application of machine learning models is, of course, natural language processing, which is all the rage right now, although those are large language models. That's a completely different set. But for processing natural language, for example, to translate a sentence, the kind of model that we looked at in the beginning with all those neural connections, it's only one way. Now, the problem is, if we are going to translate a sentence, then we need to process words in context. If the model would process the first word and then we would ask it to process the next one, without context, it would not know which was the previous one, what would make sense now, and we might as well just pick words at random from a dictionary. The result would be the same and it would be much simpler. To solve that problem, a new class of neural networks was designed. These networks have memory, and the way how they work, roughly speaking, is by having one or two additional outputs and one or two additional inputs. They are hidden in the sense that they don't conceptually belong to the normal flow of data through the neurons. And they are used so that the output of those hidden outputs can be saved and then fed to the hidden inputs when we process the next inference step. We are therefore saving data from one step to the other. This data changes naturally, but even though it changes, it means that there are some levels of context possible when the model works. The examples on the screen are about recurrent neural networks and long short-term memory networks. They both have memory. The only difference is that recurrent neural networks forget things faster than the long short-term memory networks. But the principle is still the same. Hidden outputs with hidden inputs to be used on the next step. Now, we now get to a point where this kind of network needs to output something. It works with language, so it's meant to output words. But it also means that it needs to have a vocabulary, pretty much like the first example we saw, which had a predetermined number of categories. These networks, they have a predetermined number of words they know about. It's their vocabulary. And what they are going to do is that at each step, they are going to output a vector with the probability of each of that word being used at that step. You can imagine that if we are going to calculate all the possible ramifications, this gets big very fast. Therefore, one of the possible strategies to deal with this is to use an algorithm such as the beam search algorithm, which is a graph searching algorithm. And the logic is that at each step, we look at the words and we pick the most probable ones. We forget about the others. We then run the next inference step with the most probable words from the previous one. Then we get, again, the most probable ones, we form sentences, and we keep on going. When do we end? We end when the model stops producing new sentences, or when we just reached whatever limit it was that we set for the maximum number of iterations. We don't want to end up in an infinite loop after all. We will then have a set of possible sentences, and we just pick the most probable one. The model we are going to use in this demonstration is the show and tell model. It won the Common Object in Context challenge in 2015. Now, this challenge is, of course, a machine learning challenge. The goal of the contestants is to produce models, and whoever describes better the scenes wins. This model works, again, as a cooperation of two models. One is a convolutional neural network, which translates the input image into, guess what, an embeddings vector, pretty much like we saw for face identification. Same principle. That embeddings vector is then fed into the language long short-term memory network, which outputs word probabilities, and then we repeat that process on the long short-term memory network until we get sentences. The end result could look something like this. We get a picture of a kitchen, and the model says, well, that's a kitchen with a stove, oven, microwave, and a sink. If we pay attention, there is no microwave whatsoever in the picture, which means the model was already hallucinating. But, well, it's messy enough to fool the model, I think. It was my kitchen in my previous apartment, by the way. Now, once again, we are using a pre-built model. Now, this model has a lot more scripts to work with, but what I want to show is the conversion of this model into TensorFlow Lite. This one is a bit more complicated because the author has provided a snapshot in TensorFlow. Now, a snapshot is something that you can do while training. So you run your model for some epochs, you make a snapshot, you evaluate, okay, not good enough, then you continue training, get another snapshot, evaluate, and so on and so forth, so that you don't lose what you have trained before. These models can take thousands of hours to train on quite powerful hardware, so you really don't want to start over unless you really need to. And it got to a point where the author said, okay, this looks good enough, I'm going to publish the trainable model so that people can pick it up if they want to. Now, we don't want to, which means we needed to first run a step known as freezing. So the model can be used for inference, and now we can convert it. Now, conversion in TensorFlow Lite means instantiating the converter. In this case, it is from a frozen graph. It can be from a saved model. And we tell the converter which are the input tensors we want to use and the output tensors we want to use. This information comes, of course, from the model itself. Either you built it and you know what they are, or the author has published those. The first conversion that we run is to build the image processing model. We give the tensor names, and we not only specify the default optimizations, but we also specify a data format. Now, this is interesting. Remember that I mentioned earlier that with TensorFlow Lite, we can customize the model for the specific architecture of the platform we're going to run it on. And in this case, by converting the numerical amounts used in the model into a 16-bit float encoding, not only the model becomes a little bit smaller, but it remains suitable for acceleration using the neural network API. If we would be running this model on a processor that only supported, for example, integer arithmetic, then we would request integer quantization. Now, you can say, well, but that is going to change the model's output because it loses precision. True. And this is why models also need to be evaluated after conversion. But hopefully, this quantization process will not alter the model's behavior in a very significant way. It's always a compromise, after all, if we run models on less powerful hardware. And then we repeat the process. We convert the model that is going to handle the long short-term memory network. Going back to Android, working with the model itself is, well, again, same old, same old. This time we have two models, so we map the files into memory and we instantiate an interpreter. In this case, the options applied were not only enabling the neural network API support, but also specifying that we want 4 threads for this processing. Now, ideally, this would be interrogating the Android operating system to know the number of cores and adjusting the number of threads accordingly, but, well, we are looking at the sample anyway. And then we have two operations. Image processing, same principle as before. We provide the input tensor and the output tensor. We use a different technique for identifying which tensors we are working on. In this case, it's working with tensor indexes. It's just a different technique. And the inference step has a few more lines, but they all handle buffers. Running it is again the same principle, input, output. But now we have two inputs and two outputs. One of them is the new data that's being processed and the word probabilities, and the other one is that state I was talking about that allows each inference step to behave based on the state from the previous step. What we do then is we process the image, we got the input vector, and then we just loop with, well, the help of a beam search class, but basically we loop, finding the top values, finding the top words to form sentences. What is the end result? Well, the end result is something that will hopefully be correct or interesting. Now, if the network cooperates, hopefully, there it is. Well, it says that this is a laptop computer sitting on top of a wooden desk. I would say that's pretty accurate. If I now take a picture of the audience, let me see something that does not have too many reflexes. So, and now I wonder, what is it going to say? It says it's a group of people, that's correct, sitting at a table, not really, with laptops. Does anyone have a laptop anywhere? No? It got it mostly right. And this is the funny part with this kind of models. We should always remember that the models only know what they were trained with, which means that if no one trained this model with pictures of people in an audience, then it really does not know what it is. I would say that it was good enough that it already identified that people were present. That's a good step. Another, and the last example we are going to see today, is the usage of something called a generative adversarial network. A bit of a mouthful. The generative part already gives it away. It is going to generate data. It can be used, for example, to restore data. Let's say we transmitted something, packets were lost, and it may be possible to use a model to try to infer what was there before. Very CSI, I know. Or simulations. If we are running, I went to a talk about a smart city yesterday. Let's say we are simulating traffic in a city. It is possible that someone builds a generative adversarial network model to simulate cars moving around. In our case, we are going to apply photographic effects. And the adversarial part in the network comes from the way how they are trained. Because in fact, we use one model for generating data, the generator, but for training, we need an additional model, the discriminator. What's the job of the discriminator? The discriminator is the one who is responsible for detecting whether the data it receives is fake, meaning whether it was created by the generator, or if it is real. So there are two steps in training. The first step, we train the discriminator. We show it real stuff and generated stuff so that it learns to tell them apart. Then we stop training the discriminator and we train the generator. And now the generator's job is to produce data that is so good, the discriminator starts thinking the data is actually real. When that happens, then we repeat. We train the discriminator again, so it gets even better. And then we train the generator again, so that it gets even better. Until such a point when we are happy with the results. Now, from a theoretical perspective, this process should reach Nash's equilibrium, which is basically a point where all parties have the same abilities, they cannot really improve, they are equivalent to each other. In practice, it doesn't really happen. And it works just like with all the other models. We just evaluate them and see if they are good enough. But what I find really amusing here is that we do have competing models where one is always trying to outsmart the other. The model chosen for this demonstration is, again, a pre-built model, is the Anime GAN version 2. As you can probably already guess from the name, its purpose is to transform input images and give them a cartoonish look. Once again, the conversion step, in this case, it's much simpler. It is, the author has already provided a full-blown TensorFlow model ready for inference. Therefore, all we have to do is instantiate the converter, convert, and save the model. Now, when authors are really, really nice, this makes our work a lot simpler. Once again, you probably already know what you're going to look at, but we are going to look at a class that sets options, loads a file, loads it into the interpreter. And this is what makes it stand apart from the other demonstrations, is that this model has been built with a dynamic input tensor, which means that it can work with images of any size. Now, in order to use it in our application, we need to specify the size of the image we are going to work with. And we just defined some values which were appropriate in terms of processing speed and quality. Processing itself is, again, straightforward. We keep on using the Camera 2 API to capture images. This time it's not a real-time analysis. The processing is not that fast, but it is taking a snapshot and running processing on it. This time it takes a couple of seconds to run. Let's see the result of what will happen when I take a picture. Well, let's first try the laptop again. Now it is running. Hopefully by the time this reaches the laptop, you saw the processed image. There it is. I'm not sure it's very readable, but it looks more like a cartoon than exactly a photograph. Let me see if I can find some volunteers. Say cheese. Now let's see the result. Okay, so this one is more obvious that now you become a cartoon, and as you can see, thankfully, no identifiable information whatsoever, you are safe. Now, the point of this is to show you that it is not difficult to use a model in Android applications. The TensorFlow Lite library is available also for other platforms. The hard part is always building the model, and thankfully, as I have also demonstrated, there are quite nice people out there who have built models and made them available for us. Going back to books. This book was written on the 18th century, 1760 something. It was written by a priest, Monsieur de Condillac. It is a philosophical text. It deals with the body-mind duality. But what I find really interesting is that there's an example. In order to demonstrate his ideas, Monsieur de Condillac gives an example. Let's imagine there would be a statue, and that statue would be humanoid, and it would be animated by an empty spirit, or soul if you prefer. He was a priest anyway. But it is empty. It knows nothing. And he argues that if we could give that statue all human sensations, and he means this literally, he was talking about our senses. If we could make it experience senses, if we could feed it sensations, then eventually that statue would learn what it was, the human condition, just by feeding it sensations. And what I find interesting is that this was the 18th century. A couple of centuries later, this still kind of matches the idea we have regarding how we learn as children. And it matches exactly the way how we train machine learning models, which is also interesting. A machine learning model, when we start, is just noise. There are random values in there, and then we feed it data. And we keep on feeding it until finally we are satisfied that it has learned something. Well, contemporary philosophers kind of disagree with Monsieur de Condillac, but that is also a story for another time. That being said, all the code, and I mean the full code, not only the half a dozen lines I could show you in these 50 minutes, is available in a repository. That's the link. So you can take a look at it, play around if you want, get some ideas, probably look at the way how something was built, and you can feel free to shout some insults if you want to. Thank you for being here today, and I hope I have at least inspired you, or in a minimum have shown you that it is not difficult to use a machine learning model. Now, what you can do with it depends on your hardware, but it is not difficult. Thank you so much for listening.